Scientists discovered that an ordinary oyster mushroom can eat oil, break down plastic, and survive inside some of the most toxic environments on Earth. At first, that sounds impossible. Because when most people see an oil spill, they see an environmental disaster that could take decades to clean up. Scientists saw something else: food. In controlled experiments, oyster mushroom mycelium didn't just survive around crude oil, it kept growing. Some contaminated mushrooms even grew larger than the clean controls. And that forced researchers to ask a question that sounds almost ridiculous. If a mushroom can turn pollution into food, what else can it do? Because the deeper scientists looked into this fungus, the stranger the story became. Researchers began discovering oyster mushroom networks surviving in petroleum contamination, breaking apart complex hydrocarbon compounds, and even showing the ability to attack certain forms of plastic. Then came the images: floating barriers packed with mushroom mycelium drifting through polluted waterways. Scientists called them mycobooms, living filtration systems designed to absorb and break down oil spills using nothing more than fungi, straw, and time. And the deeper researchers pushed these experiments, the more uncomfortable the implications became. Because hidden inside an ordinary grocery store mushroom was a chemical toolkit powerful enough to dismantle some of the most stubborn pollutants humans have ever created. And it may have been doing it long before we noticed. When oil spills happen, the images always look apocalyptic. Black coastlines, dead birds, tar-coated water, entire ecosystems suffocating under petroleum sludge. But underneath forests, fungi have been solving a similar problem for hundreds of millions of years. Long before plastic existed, long before oil refineries, Earth was covered in dead wood. And wood is chemically difficult to destroy. Trees evolved lignin, an incredibly complex structure designed to resist decay. For millions of years, dead forests piled higher and higher because almost nothing on Earth could break lignin apart. Then, fungi evolved. Specifically, white rot fungi. Species like oyster mushrooms developed extracellular enzymes powerful enough to dismantle those molecular bonds from the outside. Instead of chewing material internally like animals, fungi chemically dissolve their environment first. They leak enzymes outward. The world liquefies around them. Then they absorb the remains. And this is where things become disturbing. Because petroleum products and plastics share structural similarities with lignin, complex carbon ring architectures that fungal enzymes already evolved to attack. Which means modern pollution accidentally resembles ancient fungal food. Humanity invented plastics in barely over a century. Fungi have had over 1 billion years to practice chemical warfare. And evolution noticed the similarity immediately. In Louisiana estuarine conditions, researchers began testing whether oyster mushroom mycelium could survive inside crude oil contamination mixed with salt water. Most organisms fail in those environments. Salt stress alone destroys many biological systems. Petroleum makes it worse. But oyster mushrooms tolerated both. Researchers studying Louisiana sweet crude observed fungal resilience against stubborn petroleum fractions that normally persist in ecosystems for years. The mycelium continued spreading through contaminated material anyway, threading itself through hydrocarbons like roots searching for nutrients. Then another experiment produced something even stranger. A NASA New Jersey Space Grant Consortium project grew oyster mushrooms directly on oil-contaminated substrates. The expectation was stress, deformities, stunted growth. Instead, some contaminated mushrooms grew larger than the clean controls. The crude oil had become an unconventional energy source. The fungus wasn't simply enduring pollution, it was metabolizing it. Imagine discovering a forest organism capable of looking at toxic industrial waste and interpreting it as calories. That's when mycoremediation stopped sounding like environmental activism and started sounding like biological science fiction. But oil was only the beginning, because eventually, researchers pointed the fungus towards something even more difficult to destroy: plastic. Plastic survives because nature struggles to recognize it. Most organisms never evolved pathways to dismantle synthetic polymers. The molecular chains are durable, stable, and biologically unfamiliar. That's why a plastic bottle can survive for centuries. But fungi don't attack material the way animals do. They attack chemically. The process begins slowly. First, the mycelium weakens the polymer surface itself, creating microscopic fractures and porous openings across the plastic. Then comes depolymerization. Enzymes like lactases and peroxidases begin dismantling the molecular chains into smaller compounds the fungus can absorb. The plastic doesn't rot normally, it gets chemically erased. And scientists are now investigating whether fungal systems may even help break down PFAS, the so-called forever chemicals linked to industrial contamination worldwide. But the visual reality is what makes this feel unreal. White fungal threads crawling across petroleum sludge, mycelium spreading through landfills, mushrooms erupting directly from waste piles humans assumed would outlive civilizations. At one point in Mexico City, oyster mushroom mycelium was introduced to used diaper waste. Within 2 months, researchers documented roughly an 85% reduction in material mass, and the mushrooms growing from the waste showed no detectable toxicity. That's the kind of discovery that sounds fake the first time you hear it. Until you realize laboratories around the world are quietly repeating versions of the same experiment, again and again and again. Most people think mushrooms are the organism. They're not. The mushroom is temporary. The real organism is the underground network. Mycelium behaves less like a plant and more like a decentralized biochemical intelligence spread through the environment itself. It constantly senses nutrients, redirects growth, adapts chemically, and explores terrain without needing a brain, which makes mycoremediation strangely terrifying. Because fungi aren't trying to save the planet, they're simply doing what evolution trained them to do: consume complex carbon structures wherever they appear. Dead trees, petroleum sludge, synthetic polymers, industrial runoff. To the fungus, these may all look chemically related. And once researchers realized that, the implications expanded fast. Floating mycobooms for oil spills, fungal filtration systems for contaminated waterways, mycelium reactors designed to detoxify industrial waste, even experimental packaging materials grown from fungi themselves, biodegradable replacements designed to disappear naturally instead of lingering for centuries. Humanity spent generations manufacturing permanent waste. Fungi may have accidentally evolved the opposite technology, but there's still a problem: scale. Because the planet is producing plastic and petroleum contamination faster than ecosystems can currently recover from it. And scientists are racing to determine whether fungal systems can realistically keep up with what humans created. The deeper researchers go into fungal systems, the stranger the pattern becomes. Again and again, fungi appear capable of adapting to substances that technically should not exist in evolutionary history. Synthetic chemicals, industrial toxins, refined hydrocarbons, plastic polymers invented only decades ago. And yet, fungal enzymes keep finding pathways into them, almost like evolution prepared for chemistry itself instead of specific materials. That idea changes the story entirely, because humans tend to see pollution as unnatural. Fungi don't. To fungi, pollution may simply be another carbon landscape waiting to be explored, which creates an uncomfortable possibility. Nature may already be building systems to survive us. Not through morality, not through environmental movements, not through human intention, but through blind evolutionary adaptation happening silently underground. The fungus doesn't care where the carbon came from, only whether it can be consumed. And underneath landfills, underneath oil spills, underneath entire industrial cities, the mycelium keeps spreading anyway. Somewhere in polluted water, a floating line of mushroom mycelium is still absorbing oil molecule by molecule. No noise, no attention, no announcement, just billions of microscopic chemical reactions unfolding inside a living network older than humanity itself. For centuries, humans treated fungi like background life, something soft, passive, forgettable. But fungi were never passive. They were biochemical engineers hidden underground the entire time. And now, scientists are discovering that some of the systems capable of cleaning humanity's industrial damage may have already evolved long before the damage existed. Because the mushroom was never adapting to us, it was adapting to chemistry. And chemistry never stopped changing.